Hello, I'm Robert from the Dresden University of Technology, and today we're talking a little bit about focusing our laser beam. So the target that we want to have is we want to decrease the beam waste exiting our laser beam source that is shown over here with a certain kind of diameter which is called R0, so for the radius, or D0 as a diameter. And we want to decrease this in order to work with the laser beam at our system. So basically what we have the beam waste at the exit of our laser beam. Then we're focusing this beam waste onto a focal plane at a certain type of focal length. And why is this important to get a smaller beam diameter? Small focus diameter or beam diameter means we have a higher resolution, and with this higher resolution, we have a higher precision which we could work with. And furthermore, the intensity is increasing, and this is needed for certain laser-based processes, such as sublimation cutting, for just like to name one example of this. And it's far more easier to reach smaller beam diameter than just increasing the laser power in order to get higher intensity. And the relationship between them is shown in this short equation here. So the intensity is nothing else as the laser power that is given from your laser source and divided by the area of the laser spot that we have. And noticeably, we have like a circular laser spot, which means that the area of the spot can be calculated by the radius squared times pi. If you have a rectangular spot, of course, then you have to use another equation to get the area of the spot, or triangular, whatever it needs. But basically, you have to need the area of the laser spot that you would need to work with and to calculate the intensity later on. And to see small spot size are always like favorable in that case, as I already mentioned, to have higher precision. And there's the issue that we got some limitations here. So there are some minimum values which we could reach, and we talk about the first limitation, which is the diffraction. And as you can see here, we have a Gaussian beam laser with a certain beam diameter D entering our lens, and we get like a smaller beam waste in the focal plane, which is not capital D, but the small d. And this small d, so the beam waste in the focal plane, can be calculated by this equation over here. So 4 times f, which is the focal length of the lens that you're being used, divided by pi times d, capital D, which is the beam diameter in front of the lens, times the wavelength. And furthermore, we have the so-called focal depth or Rayleigh length that also can be calculated using this equation over here. And this one determines how easy or how fast the laser beam is widening up. And basically what is said with, if you are within the Rayleigh length or within the focal depth, all different kind of processes are even and can be comparable to the focal plane. If you're outside of those focal depths, it means that you have a different intensity and different other physical phenomena take place. And therefore, you have to take extra caution. But if you work within the focal plane, it should be fine as well. And to get the relationship is shown over here. So if you have a certain beam waste or diameter of the laser beam, you have a certain opening angle, and this is related to the opening angle and beam waste after the focusing. So the tighter you're focusing, the shorter the focusing is, the smaller the beam size will get, but also the angle gets widened up pretty well and pretty soon, which means alongside of the beam, you're further outside of this radial length much more quicker. So you have to take extra caution when it comes to the positioning of your focusing system or of your processing head, as well as your part that you want to manufacture with. And to get the focusing diameter as small as possible, everything depends on the 3 different parameters. This is the wavelength of the laser, the beam diameter before the focusing lens, and the focal length that you have. You can as well already calculate it here with this formula. So F, so the diameter of this is like the focal length times the diameter of the first airy disk. So this is like the minimum possible diameter that you can reach, and you can calculate this diameter by the so-called area equation. So 1.22 times the wavelength divided by the beam diameter before the focusing lens. So normally it's like this, that the wavelength is mostly given from your laser source. You can't really change that. And at some processing heads, also the focal length is somehow set. So the only thing that you could change in order to decrease your laser beam is to increase the diameter, the D, before going into the lens over a collimation unit, for example. So you could say, okay, in order to get smaller focus diameter, I will increase the beam diameter before going into the focal length further and further and further, and this wise you will get smaller beams all the time. Well, this only happens until a certain point, because then we have another limitation, not the diffraction one, but the aberration. And the aberration limit is nothing else that says, okay, shown here on the right-hand side, the further I increase my beam, my rays go further away from the optical axis, which is like in the middle one. And they always have different ways into our glass that is getting focused, which means so they have a different angle and you get different focus for your different beams alongside of the optical axis here. Which means at the end, the larger the beam gets, your beam gets somehow blurry or gets smeared alongside your optical axis here. So this is like the longitudinal spherical aberration, as well as on the transversal spherical aberration. And this one somehow hinders and increases the beam because you don't get a certain point where all your rays overlap. You get a certain area. This is called the angular blur. And you can calculate also the diameter that is possible using this blur function that is shown over here. So again, we have the focal length of the lens that you're being used, and then the delta of this angular or the full angular blur. And this can be calculated over this equation over here, where D is the diameter of the beam waist before going into the lens. F is again the focal length. N is the refractive index of your lens. So this is also important. What kind of lens do you have? Different lenses, different glasses have different refractive index. And then we have the K value here, and this is the shape factor. And the shape factor is determined by this little equation over here that determines like the radius 1 and the radius 2. So depending if you have like a plane convex lens or a biconvex lens or concave lens, you have different kind of shape values. This is shown in this graph over here. So depending on what kind of optical element you're using, you get different values for the angular blur, and then this somehow either the aberration limits your focusing of the laser beam or the diffraction. In the best case, you choose your optical setup, so the diameter that gets larger as well as the focal length, so that you're at the spot that they are limited, let's say both on the aberration limit and the diffraction limit at the same time. So that would be the minimum possible optics or the minimum possible diameter that you can get with your optical system. With this one, I would like to thank you for the attention in this educational video, and I see you around in the next one. Bye.